7th, Monday, 10:45 to 12:45 here. And we are going to have the combined exam with the distance learning student. Okay. Then this is the assignment, and the Lakshmi, Dylan, the processor. Okay. So last class we have seen the different types of selection and the join. For the selection, we will take a look at again, but it is in the list of the selection approach are in the handout. Linear search, binary search, primary index for order to 5, and the primary index for the multiple record range query, and the clustering index. Then secondary index is the non-ordered column. Then the conjunctive selection, and so on. And in addition to the selection, we had different types of the join. The first one is the nested loop join. Second is the single loop join. Then third one is the sort and merge. Then final is a hash join. So we will see again. Then we will verify what is the code today. Before that, regarding to that the join operation. There are several factors you need to consider when you decide the performance. Performance means which one is the fast way. Okay? Always the main purpose, main goal of the query optimizer is try to find the fastest way. Okay? To access the data. So when we join the two tables or multiple tables, there are different types of join. In addition to that, different types of join. So also we can consider the other factor. For example, whether we have the available buffer. Why? Because when we join the two tables, the joined column should be, so for example, we have the employee table and we have the department table, and we are going to join with the DNO is equal to D number. Okay? So to use this one, the matching. Matching means the tuple that satisfied with the disjoint condition should be saved as the buffer in the memory. So how much buffer you have, the availability, especially for the hash join. Hash join we need more the buffer for each hash key, hash bucket. And also we need to consider the join selection factor. We will see what is a join selection factor. That means when we join the two tables, okay, there are different join the factor. The DNO is equal to D number, but the social security number is the manager social security number. Okay? Their join selectivity is different. Join selectivity means among the total number of combination, which means the Cartesian product. Okay? How many of them are joined? If too many joins, all of them are matched, we don't have to use the join. Instead, we'd better use the Cartesian product, because the join operation need to select to find the tuple that satisfied with this condition. So, however, if we can find if the join selectivity, that means only one column, one tuple for one tuple in other. Okay. By the way, at this time when we join the two tables, this left-hand side is called the inner table. It's the inside. It's the outer table. Inner to outer. Also, this is called driving table. It's the main table. And this is the driven table. Okay? So we are going to start from the inner table or the driving table to join with the outer table or driven table. At that time, so we are going to find how many of them are joined. Okay? Depending on the join selectivity, it will be different. So we will see how to use such a join selection factor during the query optimization. And also inner versus outer relation, which means which one will be. So which one will be driving table, which one will be driven table, which one will be inner table, which one will be outer table. Depending on the order, it will be different. So during the query optimization, so we will consider such a different factor when we join find which join option will be the fastest way. Okay, then Regarding to the hash join is slightly different from the others. It's not easy to clearly define the cost of the hash. So I'm going to skip this part, but briefly the explain about what is the operation during the hash join. Hash join basically use the hash function, then keep the tuple information to the specific external hash bucket. So for example, if we are using modular 5, so how many different hash keys? So 5 hash keys. 0, 1, 2, 3, 4. Any tuple that has the 0 hash key will store that this bucket. Where is it? This is in the memory. Then another. So we need to partition. Okay, separate the tuple, the driving table, import the tuple in the driving table, partition. Okay, then join or proving paste means for the driven table. Tuple is the driven table. We apply the same hash, the key. Then what is the hash value? Then depending on the hash value, go to for example, this one is a 0. Then go to this bucket. Then find the matched one. Okay, that is the partition paste and proving paste, or partition paste or joining paste. So we need to consider that the cost depends on the hash function. Also, it depends on the performance of the buffer area. So in our practice, we are going to set the hash using hash join, the hash key join. So we will set the cost as just 1, okay? Because it's not the static value, it depends on the multiple factor, so it will be more complicated. So we will set as just 1. Usually, we can narrow down the search area by the hash key. So like the 5, in this case, the 1/5 of the search area, so that is a benefit of hash. But if we change the hash function, it can be different. So we cannot clearly decide the static value of the cost. So instead, we will use the default value 1. That is the hash. So we have seen the selection and the join operation, the mostly. The other, in addition to such a relational algebra operation, we have project. Okay, what is a project operation? Select specific, limit the specific columns. Okay, so for that, so what kind of course we need to operate such a project operation? Depending on the output of the project, we need to eliminate duplicate data, right? Do you remember that? The relation does not allow the duplicate data, so we need to do the sorting, okay? However, in the SQL, not relational algebra, in SQL, we don't have to worry about that, the sorting one. One of the different things between the relational algebra and SQL is relational algebra does not allow duplicate data. On the other hand, SQL allows the duplicate data. SQL return the data as it is. So we don't have to worry about that, the sorting part or hashing part. So we are going to ignore such an overhead of the projection. Some other operation that we need to consider during the query optimization is the set operation, like the union, intersection, set, difference, Cartesian product. Especially Cartesian product is all the combination of the two tables. Okay, at that time it will be more costly. Okay, it's a very expensive operation in the relational algebra operation. Okay. Also, aggregate function. Aggregate function mostly require what? We need to group the data. How can you make the data as a group? So for example, I'd like to make the student group by the age. How can you do that? We need to sort the data. Then from sort by what? Age. Okay? Then it's ascending or descending from the beginning of the data. We can make them group. Okay? By age. So that requires what? The sorting operation. So we should have the very fast sorting algorithm to perform the aggregate operation. So that should be considered in the query optimization. However, that depends on the sorting algorithm you have. Another factor is temporary space. Okay? The sorting requires additional buffer. What kind of sorting algorithm did you learn? Bubble sort, quick sort, something other sort, but that requires additional space, at least one, the byte of the data. So, depending on the algorithm, their performance will be different. So, in our practice, we are going to ignore such as sorting for aggregate function. However, in real query optimizer, definitely they need to consider the sorting operation, the cost of the sorting operation for the aggregate function. Okay. However, that is the reason each and every DBMS they try to improve, enhance the sorting mechanism. Not only just for algorithm itself, but the hardware level they provide the memory-based sorting or other the fast media will be added, attached to improve the performance of the such a sorting algorithm. Okay. But in our case, to simplify the problem, our example does not include any the sorting or the such an aggregate function. Okay. Also, we are going to consider join operation. However, in addition to the natural join, we have the left outer join, right outer join, the full outer join. Okay? What is a left outer join? We will keep what is a join operation? Only matched data between this one and this one. So for example, if this one is matched, so this one is matched, only two tuples will be returned. Right? That is the join operation. The left outer join will keep all the data that the other will be null data if not matched. Right outer join is the same thing, but keep the old driven table. Full outer join we keep both sides. Okay, that is the left outer join operation. However, in our practice, we are not going to consider left, right, or full outer join. Why? Because to consider the outer join, it's the additional cost. Okay. So not only just the I/O, but this data, even though it's not matched, should be considered in the buffer. So need more buffer and additional cost are needed. However, if you can calculate the cost of the regular join, it's not very complicated. Okay, so keep your mind in real query optimizer, need to consider additional cost for the outer join in addition to the regular join. Okay, so in our practice, we will consider selection operation. Among the selection operation, we will select some of the frequently used operation in selection and the join operation. In join operation, we are not going to consider hash because hash has several the factors we need to consider. Instead, we will consider the nested loop join, sort merge, and single loop join. Okay. So these are the main operations we are going to consider in our query optimization. Okay. I'm going to skip the pipelining. Pipelining is the next one is a heuristic approach before we apply the query optimization. So go back to the first idea. There are two types of query. What is the query optimization, by the way? Go back to the beginning, the basic again. Query optimization means it's a component to decide what? Fastest way think about when you have a travel. So you will search a lot of websites, the Google.com, the travel, or the Expedia.com, and travel suite. Then what is your criteria? Which one is the cheapest one, right? That is the same thing. When we access the data, there are many different ways, as we have seen before. If you join the 3 tables, it's easily 2,000, 3,000 different ways to access the data. As if you can find a bunch of different itinerary. So when you travel to the specific, the city or the place, okay, we need to find one of the things. So we need to find one of the way to access the data that minimize the cost, okay? So how can we judge the cost? So there are a lot of things that we need to consider in computer research, but the most dominant factor is what? Number of I/O, input and output. Memory I/O, we can consider. CPU overhead, we can consider. However, comparing to the I/O in secondary storage, the hard disk drive and database is almost ignored. So you can ignore. So we are going to count such a number of I/O to determine which one is the fastest way. Okay? So, in other words, for example, we have the linear search and binary search and some other search. We calculate the number of I/O, number of I/O, number of I/O. So let's say this is a 10, this is a 5, this is a 1,000. Then we will select this approach. Okay, this is called what? Cost-based optimizer. And another approach is, instead of calculating the cost, instead of, this sometimes the tedious stuff. You need to search the Expedia.com, Obis.com, the whole bunch of different sites, and check all the itinerary. Then try to find the cheapest one. It takes a time. No pain, no gain, right? But however, if you are rich, right, if you have enough money, I don't want to waste my time. So you have the rule. Like first, if there exists any airplane to the city, that is the first priority. Second priority, if there exists any, the MTA, okay, if I cannot find the airplane, the next option is the train. The third is a bus, Greyhound bus. Last option is walk, okay? So you have the rule, from first rule, second rule, third rule, first rule. So always apply this rule, okay? This is a rule-based approach. It's the same thing in the database query optimizer. So first is if there exists the primary key, always we are going to use the primary key. If there is a secondary key, then we are going to use the secondary key. If there exists any nested loop join, yes, that is the third option, something like that. So we have the list of the rules. That is the rule-based optimizer. So this rule-based optimizer is a naive way. It's obvious. It's a trivial. We can just apply the rule. The most important thing is how to decide the rule. So each DBMS, RDBMS, has their own list of the rules, but usually they are starting from the primary key that end with linear search. Okay? So we don't have to worry about too much. So we will see later the difference between them. Then we can, nowadays, most of the system use CBO, cost-based optimizer, based on this approach. Okay? Before we apply, one of the problem of the cost-based approach is how many different ways to access the 3 tables. So 3,000, let's say. So we have case 1, case 2, case 3,000. We need to calculate the cost. As if we are struggling to find the best itinerary. So I need to be this one, print out. So a bunch of files among them we need to. So it takes a time, it's a tedious job. So same thing. Sometimes there are obvious cases we can ignore, right? For example, when you travel to the Manhattan, are you going to use the airplane or private jet? No, nobody want to use the airplane to travel to Manhattan. It will take a longer time sometimes. So, obvious case we can eliminate. Then we can narrow down the 3,000 to the 10,000. 3,000 to the 1,000 case. And also, first, there's no other way to take the train at UB. We need to walk, okay? We need to get the taxi first to go to the Bridgeport station, okay? No other way. So, obvious case, we can apply, okay? Otherwise, if we go to the New Haven station, no, that's not a good way. So, obvious case, we can apply, then narrow down the 10 different case, then apply this cost function that we are going to discuss. So, this approach to minimize or narrow down the cases, that is called the heuristic approach. Before we apply the cost function, heuristic approach. Idea is, what is our goal of the query optimizer? To find minimum cost. Minimum cost means minimum input and output. Okay? So idea is very simple. For example, one example is, we'd like to select the first name, last name, and the department number from employee and department, where manager SSN equal SSN. Right? We can display the manager information per department, right? It's a simple query from the company database. Then there are two approaches. Check which one will be better. So we decide to join employee first, department. This one is also employee and department. But as you can see, we have a projection operation. Okay, we have a projection. So this approach, keep all the data first join, then apply first name, last name, and DM here. This one, first apply projection. Which column we need? First name, last name, DNO, and social security number. This one apply DNO, D number, plus manager SSN, and join. Which one will be better? This one or this one? Second one.
We have already filtered out the required tables.
Right? Which means we don't need all the column. To keep all the column, you need to read and save in the memory. So it's an additional cost, right? So unused data, we don't have to keep forever. So in other words, why don't we filter out unused data as soon as possible? Okay? Join is the same. When you join two tables, not all the data will be used. So if possible, why don't we apply the join operation that can eliminate, that can filter out unused data as soon as possible. That is a heuristic rule. So during the parsing level, so we can change the order of the operation. However, that should not hurt output. So as you have seen before, in the relational algebra operation expression, how many different ways to implement your relational algebra expression? So each student may have the different answer, right? So it's the same thing. There are a bunch of different ways to access the same data. So we can filter, we can apply the operation that can filter out as many data as possible. That is a heuristic approach. Let's see the example of this one. This is you already seen the before. So for the project Stafford, okay, we'd like to retrieve the project number and controlling department and manager information. To do that, we need to access the project, department, and employee. Okay, how many different ways? So let's see. To quickly check how many different ways of accessing the such data. D represent the department, E represent the employee, and the project. Okay, let's say for each table, we have the linear search. Okay, and also we have primary index. We have the secondary index. Okay, let's say 3 of them. One more, cluster index. So 4. So 4 different ways. We need to select one of them. This one, same thing. 4 different ways. 4 and 4. Okay? So how many different combination of them? 4 times 4 times 4. 64, something like that. Then, for join, we need to join 2 tables, right? So how many different ways of join? Nested loop join, and single loop join, and sort merging. So we are going to ignore the hash join. So that's the 3 different ways. The 3, and also this one has the 3 different ways of join. So 3 times and 3. That's it. And order, each one will be the DEP or DPE. And how many different ways? So 3 factorial, right? So that is a very simple statistics. That's 3 factorial. It's just 6. So total, how many different ways? This is the, how much is that? 64 and 128 times 27, right? So you can see it's more than 1,000 cases. 1,000? Anyway, so many different cases. If you have the more index, secondary index 1, secondary index 2, secondary index 3, there are many, many different ways. So easily, it's let's say 1,000 different cases. Instead, why don't we apply the heuristic approach? So for this, first we are going to have query tree. Query tree, we have seen what is a query tree after relational algebra and relational calculus. We can make the tree structure for operation and the relation. Like this one. Why don't you take a look at it? So most simplest way, join P and D. P and D first, Cartesian product. That's all combination. Then Cartesian product with the E, this one. Then apply any condition, join condition, and any condition will be applied to here. So it's a D number, it's a join condition, and P location, selection condition. Then finally apply the output. The output is the same as the other, right? However, the problem is you need to keep all combination, all the Cartesian product to the memory. All Cartesian product to the memory. Then apply the selection, you need to still keep the whole attribute, then finally projection. It's overhead and takes a longer time. So heuristic approach, try to apply any operation that can minimize the output. For example, why don't we apply the selection first? Selection, so we don't have to keep all the employee information, then only that satisfies this one. Okay? Then for the join operation, instead of the applying the join operation very last, apply as soon as possible. Then finally we can have the output. Then we can minimize the the cost. That is a heuristic approach. Then, using this one, if we have the several option cases, then apply the cost-based optimization that we are going to discuss. Okay, this is a heuristic approach. So you can keep the idea only, the heuristic approach. So apply the operation as soon as possible that can minimize the output. So that is a heuristic approach. Then finally, we are going to see the cost-based query optimization. The main issue is how to calculate the cost for each operation. Okay, so that is the cost function. Many of them are not standard algorithm, which means it's the same as the other. Okay, linear search is always the n/2 or n. So no matter what types of RDBMS you use, it's the same thing. However, sometimes the different factor will be applied. We will see the general, the cost function in this example. Any questions? Okay. There are different factors we can consider. However, we will consider only the storage cost, which means I/O. It's I/O. Access cost. Oh yeah, this one, number one. The other we can ignore. But some of the DBMS consider additional cost, but it's a trade-off. If you precisely consider all the research, the cost, it will take a longer time to decide. Okay. The most of the cost-based optimizer consider input and output. So to do that, these are the notation that we are going to use. It's the same as the same notation that we have seen in the indexing structure. So small r means the number of tuple, and the capital letter R means it's the average record size. If we are using the variable length, the column, it will be various, so it's average. So B is the number of block, because I/O means it's a number of blocks that you need to read and write, right? So not the record. So we need to count the number of blocks instead of the number of record. So B is our main target. So however, we need to calculate how many blocks we need to access, how many blocks for employee table, how many blocks for the department, using the blocking factor. Blocking factor means average number of records in one block. Okay. Then additional information. So basic approach to read the data file is a table, employee table. We need to access indexing first. For example, if we are using the B+3 index, so level 1, 2, 3, and 4. So if the level is x plus 1, something like that. So that is the level x for each index. We need to keep track of the level. So level is important. And first level index block means when we have such a B+3 or any tree base, this is the first level. How many? The index, first level index block. Why? Because if we are using for example, where the SSN is bigger than 1111, it's a range query. Using sibling pointer, we need to access a number of the index block, the first level index block. So we need to keep the information about how many first level index block. And also, number of distinct value means in where condition SSN is equal to 1111. In another, where condition is when we return the data, is it the same? This one return only one record. Okay? This one will return many records for the employee. Because it's a cluster, there is a group. This is a primary key. So For this one, definitely we'd better use primary key index. However, for this, if we are using the primary key, that is the social security number, we cannot get the data at one time. Instead, we need to access more. So this one, we cannot get the benefit of primary key index. So primary key index is not always the fastest way. Primary means it's a representative of the table itself. This depends on the rare condition. So how can we differentiate such a thing? How many distinct values? So in this column, social security number, distinct value is the same as number of record because it's a unique. What about this one? Even though you have 1,000 employees, distinct value is only 5 departments. On average, 200 data will be returned, even though you are using equality in your condition. So, depending on the distinct value, you need to decide which way is the faster way. Okay, not primary key is always the fastest way. Depending on your condition, it will be different. That is called the distinct value. Then, at that time, selection cardinality means how many data will be returned when you use this column. In this time, how many data will be returned? Only one. In this case, 200. That is called selection cardinality for that attribute. Then at that time, selectivity means this one is, for example, we have 1,000 record and this one is 1 of 1,000. Right? This one is how many different value? It's a 1 of 1,000, so this is called the selectivity percentile. And what about this one? What is the selectivity of the DNO? This is a 20%. Okay, only 5 the different value. Okay, so 20% the selectivity. Okay, of your data. So our goal is to find selection cardinality. How many data will be returned when we access the tuple using this column? So we will see more details soon. So we are going to start from the linear search. Okay. So, any more? So, hand up. It's a summary of the textbook for your better understanding. Okay, so first, the linear search. So we have learned the 8 different ways of the selection. Among them, we are going to see some of them. First one is the linear search. What is the cost of the linear search? Linear search means if we have the employee table, this is an employee table. Okay? So for the, by the way, we have the sum of the, that's the next thing. So, employee table. Then, how many IOs are needed to access this employee table? Number of tuples? No. This table is a block based. If we have 1, 2, 3, 4, 5, 6, 7, 8 blocks, it needs 8 IO. So at that time we can say the cost is 8. Okay? So number of blocks is a B, as we have seen the previous slide. So cost of the linear search, that is to say C. Cost, the first approach is 1. S1 is B. However, if you select the data using select employee where SSN is equal to 11111. You don't have to read all entire block, right? Once you find the 1111, you can stop it, right? So if you are lucky, you can find the data from the first block. If you are not lucky, it will be last block, right? What is the average? So B over 2. So that is the reason. So B over 2. Okay? But in case you are not lucky, it will be the entire block. The B block you need to read. Okay? So that is the B over 2. Okay? Then, what if? So the table is ordered. This is an ordered file. In case of ordered by the social security number, that means we don't have to use the brute force way, linear search. Instead, we can use binary search. Okay? What is the cost complexity of the binary search? So log n, right? Do you remember that? It's the number of the data. In this case, if we are using the binary search to access data, what will be n? R, number of tuple. This is a block. Okay, always block by block. So it will be b. So cost function is log 2b. Okay. So that is the, for equality condition, it's a log b. Then, what is this one? What are they? In case this is the range query. First, this is ordered, so 111 is here. Then you need to read entire tuple after that. After you find log the b based on 2, then you need to access all the other tuple. That is the S is the what? It's a selection. This is the range. This is a, in case it's not primary key. Okay? In case it's not primary key, there might be several tuples that satisfy with this one. Like for example, DNO is one. It's sorted by the DNO. Then 1, 1, 1, 1, 1, 1. How many? Is a selectivity. Okay? Selectivity, let's say it's a 200 record. I'll match it with the DNO is equal to 1. Then divide by the buffer, the block factor. Okay? So we are going to count number of the blocks that include that condition. That minus 1 means it's not because it's a ceiling, then always they should minus 1. Okay? So that is the log the b based on 2. This is the case of non-primary key. In case of the equality, primary key, unique key, primary key, then we don't have to read the further block. Okay? Only that block. So that means log b based on 2. That is based on the binary search. Okay? Can you differentiate this one and this one? This is the only unique or primary key. This one is non-unique. Okay? Non-primary key case. The third one, we are going to skip the hash instead. So in case of the hash, we will set as a default value 1. Okay? Then the primary index. What is a primary index? So this is ordered by social security number first. If one of the problem of the binary search is, it's not like this. The more data you have, the longer time it takes. So if you have the 10 millions of data, still binary search is taking longer time. How did we address that problem? We make the index of that column, so that is the index. That's this one. So how many levels of index? X plus 1. Why 1? Because 1, 2, 3 plus 1. 1, 2, 3 plus 1. 1, 2, 3 plus 1. So that is the reason X plus 1 for the primary index. It's not B plus 3 index yet. Okay, it's a primary index. Okay. The next one is, in case of a multiple record, which means like the DNO is equal to 1. It's ordered by DNO, so we have the level of a primary index for the DNO, X plus 1. However, because it's a multiple record, we need to read more. Okay? So that is if we are lucky, only one that block, otherwise we need to read all of this block, so average B over 2. Okay, so difference between the S3 and S4 is S3 is only one block for the data block, and the S4 is a primary index, but it's a range or the multiple record, so we need to read the rest of the block. That's the average B over 2. Okay, the next S5 is a clustering index. It's a DNO. This is a case of the DNO. So DNO is case level plus the specific, the block, then how many of them? Okay? How many of them are actually is X plus 1 plus this minus 1. So we can eliminate. So you have seen this example for this. Okay? The ceiling of the ceiling S over B, buffering the block factor minus 1, but here is a X plus 1, the S over the block factor minus 1, so we can eliminate the 1 minus 1. Then finally we can have the cost function for clustering index. Okay? Then this time S is how many data are returned on average when we access the data using that clustering index. Finally, B plus 3 is a secondary index. We have the primary index, but additionally, for the non-sorted column, non-ordered column, we can make the index that is based on the B plus 3 that we have seen. Do you remember the B plus 3? It has the internal node and leaf node. And leaf node, through the leaf node, we can access the data. How many? X. Then plus S means we need to, for example, we have the B plus 3 here. Sibling pointer. Then 1, 2, 3, access the data. Okay, depending on the selectivity. Okay, not always this is where SSN is equal to 1, 1, 1, 1. It's just one case. Okay, however, what about the DNO? Is equal to 1. DNO may be several the data, so it will be based on the selectivity. Okay, X plus S. Then in case of the range query, for the range query, the benefit of using the B plus 3 is first find the block, then we can use the sibling pointer. We don't have the up and down, just the sibling pointer. So X plus, this is the block. How many blocks in the leaf node? On average, we can access half of them on average. So that is the reason half of the first level index block. For each, we can access the record. That is a half of the record. Okay, so that is the reason. The cost function of using the B plus 3 in general is X plus the first level, half of the first level block, and the half of the record. What about the conjunctive? Conjunctive is a combination, right? In case of combination, you can decompose, then calculate the cost for each, okay? Then, let's see the example. So we are going to use the same company database. You already very familiar with that. These are the information we have in the database. So how many employees? How many tuples for the employee? So 10,000. And how many blocks are needed to keep the employee? 2,000, which means how many the record per block on average? 5, which means 10,000 divided by 2,000 and silly. Okay, then we can have the 5. So that's the information we have. So first, we are going to access the data using, so for example, select. Example of this query is select the employee where the assessor, this one. This is a given query. Okay? So there's no join. So how many different ways to access the employee using this condition? We can do the brute force way. Brute force way, first, what is the cost to access employee data using the brute force way, linear search? It's a B over 2, right? What is a B? It's a 2,000. It will cost 1,000 the I. Okay? Then we can use clustering index on salary. Even though this query does not include the salary, but who knows? This may be faster. So we decide to use the clustering index. Okay? Then we need to know, I think that this is the information. The query will be later, so we will see details, the case later. Okay? So these are the information about the index that are created for the employee. Okay, it's my mistake. So this is the table information, the data file information. These are the index information. First, we have the clustering index on salary. Okay, so that has the how many levels? 3 levels. Okay, 3 levels and cardinality. What is the cardinality? Per data. So for example, we have the 10,000, the salary. 11,000, how many different? Okay, we don't know, but each salary on average 20 employees. This one 20 employees. Okay, each value of the salary has on average 20 record, 20 employees. In other words, if we divide by 20, okay, that is 5,000, which means 5,000 different, 500 different salary are there. Okay, so that is the selectivity of the salary. Okay. Secondary index. We have another index, a secondary index for the SSN. So secondary index means this is a P plus 3 index. How many levels? So 4, which means it looks like the 3 internal levels and the others are leaf node. Okay, so that is the 4. Okay, definitely selection selectivity is 1. When you select the social security number, it will return only 1. There's another B plus rule index, it's a 9-key attribute, DNO. Okay? For the DNO, it has X level, it's a 2, only 2. So one internal, another one is leaf node. Then, how many leaf nodes do we have? 4 leaf nodes. That is like this one. Okay, 4 leaf nodes. And D, how many different value of the DNO? 125 means 125 department. Then, what is the selectivity using DNO? It's a 120. You can divide by, right? This one. Then, on average, how many employees per department? It's 80. Okay, that is the selectivity. And there is another secondary index on sex. How many different values of sex? Male and female. So 2 different values, 2 distinct values. And when you select one of the value, like the female, how many female? 5,000. And how many male? 5,000. Selectivity is 5,000. Level is very simple. It's a 1 level. Okay, it doesn't need any internal level. Okay, using this information, we are going to optimize the query. So first query is like this one. From employee, where SSN is equal to 1, 2, 3, 9. When you submit this query, what happened? Scanning, parsing, validating. Okay? Then binary code after compile. The binary code will be submitted to the query processor. Then query processor need to optimize this query. To do that, this SQL will be converted into relational algebra expression. One query block. Okay, this is a one query block. Then, using this one, we are going to find as many cases as possible. We are not going to consider heuristic approach here. Okay, as many as possible. What kind of option we can use? We can do the always brute force way, linear search. So let's see the example of this one. So S1 we can use. What about the binary search? Can we use the binary search? Because there's no mention about the employee table is ordered, right? We cannot, unless data is sorted, we cannot use the binary search. So binary search is not possible. Primary index, definitely not, because the data is not sorted. And S4 is not possible. S5, clustering index. We need to use the clustering index because clustering index we have here. However, that column is for what? Salary. It's a salary, the clustering index, but salary is not included. So we don't have to use salary. If we want, you can do that, but probably it's definitely not the optimized case. So we are not going to use a clustering. What about the secondary index? We have the secondary index for the social security number. So we can use the S6. Okay, it's not conjunctive, so we can consider case 1 and case 2. Case 1, what is the cost function? B over 2. What is the cost function of the secondary index? X plus 1. X is the level. What is the B? B is the 2,000 divided by 2 is the 1,000 I. What is the X? X is the number of level is a 4. But it's a given information. So it's a 4 plus 1. It's a 5 ion. So which one will be faster than others? As 6 is definitely faster. So 5 is much, much less than 1,000. So Query Optimizer will select this as the fastest approach. Okay, then we access it, then makes the execution plan. Execution plan means so kind of the itinerary, so map to access. First, access the employee table using the secondary index. Okay, then your DBMS engine execute based on the plan. Then return the data to the user. Okay, that's how it works. So this will be selected.
Professor?
Yes.
Why can't we use primary index?
Primary index is only in sorted ordered file. Okay, so don't be confused. Primary index and primary key are different. Okay, primary index means for the only ordered file. Okay, like for example, name. Name is not the primary key, but you can make the data file, ordered file, the name. Then you can make the index for this one using the ordered column. At that time, this is called the primary index. So primary index is working only when your data file is ordered for that column.
How do we know if the data is ordered?
It depends on your DBMS. In our DBMS, it's not ordered file. Okay? Most of it's a good question. What about the commercial DBMS, such as Oracle Informatics DB2? Do they use the ordered file? Actually, not. Instead, they are using mostly 99%. They are using secondary index, B+3 index, even for the primary key. Exception, your second project. What is your second project? Index organized table. It's a table but organized by B+3, which means it's already sorted in the data file. It's a very special case, specific case. Okay? However, the traditional, the DBMS, they are using ordered file a lot. At that time, we can use the binary search for the primary index. Because of the name, the students are confusing primary key and primary index. Primary means primary for that ordered column. Okay? But in this case, it's not ordered. There's no mention about the ordered file, so we cannot use the primary index. Okay? Then next, that's the same thing, but query is like the DNO. It's bigger than 5. Always we can use this one, brute force. Okay, linear search is always possible. Like you can always, even though no matter how it costs or whether or not you have the money, you can always work, right? You can include the working as an option always. So that is a brute force way. Then, what other option we can use? There's no the ordered file, so we cannot use the primary index, but binary search, primary index. But we can use, so DNO is bigger than 5. The clustering index cannot be used. Clustering is the index also ordered file, ordered by DNO, but it's not ordered by DNO. Instead, we can use the secondary index for DNO. As you can see, we have the index for DNO. We can use this one. Okay, level 2, the first level in the leaf node, full node, and distinct value is the 125 and selectivity is the 80. So what is the cost function? S6 is the x plus. We can select the second one because this is not equality. You can see that it's a range equality. So x plus the leaf node block half plus r divided by 2. So level is a 2 plus how many block? Leaf node block 4 divided by 2 plus how many record? It's still 10,000 divided by 2. So 2 plus 2 plus 5,000. So 5,004. And also here, because it's a range query, you need to always read to the end of the block. So this should be B and 2,000. Okay? Which one will be better? Which one will be selected by the query optimizer? First one, second one? First one. This is the good example of the counterexample of the using index. Mostly people believe using index is the faster. Not always. This is the example. Even though we are using the index, this is not a good case. Okay? Even though we have the index, the brute force way is faster. Okay? So that is common, really common mistake, especially in the data warehousing or batch job. That sometimes the indexing, using index is slow. Think about the textbook. Okay? Textbook, I need to search. I need the Professor Lee give the homework to find the definition of the 100 keyword, 1,000 keyword in the textbook. If you are using the index, so 1,000 times you need to go back and forth, back and forth. Instead, why don't we look up from the first page, then check each and every page has a definition, right? At least one, for example. So without the using index is faster. That is the example of this one. Okay. The next, what if the equality? It's the same thing for the first case, but the cost function is different, right? This is a range query. This is the equality. So equality, in case of the equality x plus, we can access only selectivity. Okay, that is the how many? The tuples per department is 80. Okay, so 2 plus 80, so it will be 82. So this will be the plus 80, so 82. So by changing only the logical, the equality and inequality, which one will be selected? Using index. Okay? So that is a good example to show whether or not we need to use the index or not. This is a common mistake in the real project. Many of the developers who do not have the experience, they keep asking to the administrator, I need the index. I need the index to make it faster, but that may decrease the overall performance of your system. Also, it's not faster actually. Okay, so you'd better find the different ways or rely on the query optimizer. Any question?
Peter?
Yes.
I don't know how do we operate in the real database.
Real database, that's a good question. Who will answer the next class?
Right.
Do we need to consider this? Mostly none. Who is in charge of that? Query optimizer. Okay? Also nowadays, the DBMS companies such as Oracle Informatics, they try to kind of make the system abstraction level, hide such information. Why? If you need to know this one, it will be more complicated, right? So, however, the problem is, if you do not understand this, I try to use the index, the primary key index, but it's just getting slower, but you don't know why. But if you understand how it works, the query optimizer, you can understand why the system is slow. One of the common mistake is, actually I didn't explain the several important things. The one answer is, for example, who provided this information? Without this information, can you calculate this? Even system cannot calculate. Even query optimizer, the perfect query optimizer cannot do anything without this information. Which means one of the main jobs of the database administrator, keep refresh, keep update this information. Problem, how do you get the number of data? How do you get number of blocks? How do you get all this information? Suppose that we have the 100 petabyte size database. Can I collect all the information? No, it's not possible. It takes a long time to collect such information. So you need to do the smart way. Like the sampling. We can access only 1% of the data to guess, estimate. So DBMS company need to provide the better approach to the provide the statistics. And also, it's your job as an administrator to keep updating your system. If my system is read-only database, you don't have to do the job every time. However, if your system is updated weekly, okay, mostly weekly updated job, then you need to update such a data every weekend, something like that. So that is the one thing. So what we see, do I need to know? Yes, it's better to know, to understand how my query is working and in case problem, okay? Otherwise, if you are lazy, I don't care, okay? Then you can just make the query, then the try and error, or sometimes you need to keep fighting with your administrator. Okay? So that's the thing. We will see the later more about that. What about this conjunctive? We can make the DNO is equal to 5. Salary is bigger than 30,000. Sex is equal to female. All different cases. Then find the fastest way. In this case, using the NO is equal to 5 is the lowest cost, fastest way. So we will use the DNO, the B plus 3 secondary index for the DN in this case. Okay. However, I actually skip the composite index part. If we have index, DNO is equal to 5, salary, and sex, then that maybe, not always, maybe faster. Okay, we need to calculate the cost also. Okay. What time is it? 11? 45, okay. Then, let's quickly, we will see again the next class. The next one is, so I actually simplify the problem of the query optimization. We cannot consider each and every. Actually, the most difficult part of the RDBMS, including Oracle and Informatics, they try to make it better and better, the query optimizer. It's kind of, somebody consider the query optimizer as a brain of the RDBMS. So we are going to consider core part. It's a simplified, but still it's the most important part. The first part is a selection. Okay, access the one table. The second part is the join operation. As we have seen before, what is the main part of the designing relational database? Decomposition to remove duplicate data. Because of that, we need to join a lot. Unfortunately, join operation is a very expensive operation, so we need to calculate the cost for it. To do that, one problem is when we decide to join two tables, department and employee, how many of them percentile of the matched one? Okay? If they are not matched at all, which means 0%, the join selectivity, we don't have to use that as Cartesian product. Also, if they match 90%, which means most of them we don't have to use the join operation. Instead, Cartesian product is better. Okay, so to represent that one, we should keep the join selectivity any two tables. So that include R and S means left hand side driving table, S is the driven table. So for the left hand side and right hand side, and so how many of them are matched? Divide by total number of combination. Okay, so which means it's for example we have a 100 R and 10 S, and how many Cartesian product? It's 1,000. Among the 1,000, how many of them are matched? So let's say 5. Then 5 over this one. This is join selectivity. Okay. So join selectivity should be managed here. Okay. Then how many tuples will be returned? Join selectivity times I times F. So number of R, number of S will be the estimation of how many tuples will be returned. Okay, using this one, as we have seen, there are three main different, the join operation, nested loop join, single loop join, and the sort merge join. Okay, so we will see each case, then cost function, and we calculate the cost of the example query. Okay, then finalize the query optimization. Okay, let me call your name quickly. Guo. Okay, and Jie Zhao. Okay, Junie Zhou.